The end of our text deals with radical chemistry, which is fundamentally different than the reactivity that we've discussed in the rest of our text. With radicals, we have single unpaired electrons that need to react with exactly one additional electron. These free radicals tend to be highly reactive. This means that the concept of nucleophile and electrophile doesn't apply to this type of reactivity. Our arrows look a little bit different with radical chemistry too. Because we're only moving one electron at a time, the arrows we draw for these mechanisms are always drawn with a single barb, rather than the two barbs drawn for moving a pair of electrons from a nucleophile or base to an electrophile. Look at the examples shown. In each case, a bond containing two electrons is homolytically cleaved, meaning the bond is split equally so that one electron goes to each side of the bond. Two arrows with single barbs are used to show the formation of the two radicals. You talked about this type of cleavage in general chemistry when we talked about bond dissociation energy. Bond dissociation energy is the amount of energy it takes to split a bond evenly between two atoms. Homolysis or homolytic cleavage. Most of the bonds that we have talked about in organic chemistry are most reactive due to their polarity. They are not very easy to break evenly. And so, radicals tend not to form very easily without a radical starting point. Take a look at this table. Which three bonds can be homolytically cleaved most easily? What's similar between the bonds with the lowest bond dissociation energy? Bonds between carbons also require very high energy to homolytically cleave and do not form spontaneously. Notice that the bond dissociation energies are generally a little bit better than with hydrogen, suggesting that carbon radicals are slightly more stable. It really doesn't matter what is around them. The bonds between carbons are difficult to cleave homolytically. Again, notice that the lowest bond dissociation energies at the very end are when homolytic cleavage leads to a resonant stabilized radical, either by an alkene or by an aromatic. This fourth table is the Goldilocks zone of bond dissociation energy for free radical formation. Particularly, the bonds between two electronegative atoms will have drastically lower bond dissociation energies and therefore form radicals much more easily. Things like peroxides and molecular halogens. Energy in this range can often be supplied with light and sometimes even with heat. Whenever we supply light, it typically is a broad range of wavelengths. Because of this, the weakest bond, which requires the lowest energy light, is typically the bond that is able to homolytically cleave to form the radicals. We will never end up with a hydrogen radical when we have the possibility of forming a halogen radical instead. Bonds that are particularly able to radically cleave are often used to start a chain of radical reactions. We call such molecules radical initiators. We've already seen in our tables that Cl2, Br2, I2, F2, and peroxides are simple molecules that can readily cleave and form radicals. This is even more true of special initiator N-Bromosuccinimide, also called NBS. The NBR bond is weak, and the N radical is even more stabilized by resonance. 2,2' azo bis isobutyronitrile, also called AIBN, forms similarly stabilized radicals that release nitrogen gas and can't recombine, making it also a powerful initiator. Although radicals don't readily form between halogens and carbons, the amount of energy required to form them gives us some insight into their relative stability. Tertiary radicals are much more stable than secondary, which are more stable than primary. Notice that this stability trend follows the same pattern as the stability of carbocations. We can see the same thing graphically. The energy jump to the tertiary radical is much easier than the jump to any other radical. Remember, carbocations are more stable when more substituted because the substitution can donate electrons to the electron-poor carbocation. A free radical is electron-poor too, just like a carbocation, so the same thing stabilizes it. We also see the same trends as we change hybridization. sp radicals are drastically less stable than sp2 radicals. Conversely, we see dramatic increases in stability when resonance forms exist for a radical. Notice in the bottom resonance hybrids, the arrows that are used for converting between resonance forms are formed differently, but the way in which a radical moves is essentially the same as the way a carbocation moves. In radical resonance hybrids, it isn't charge density that's shared between locations, but instead electron spin density from the unpaired electron, which you can see as blue in the diagrams on top. Just like with reactions involving paired electrons, radical chemistry has a set of elementary steps. The first step is generally homolytic cleavage, which is often also the rate-limiting step since it's typically high energy. It's also most often the initiation step. Radical reactions can occur without some sort of source for the radical. The reverse of homolytic cleavage is radical coupling, where two radicals combine to form a stable, not radical product. These are also called termination steps, since they end the reactivity of each radical. Once a radical is formed, that radical will try to react with whatever else it can find. One mechanism will extract an atom from an existing sigma bond and leave behind a new radical. These bimolecular homolytic substitution, or SH2 reactions, are also often called propagation steps because a new radical is produced even as the old radical is stabilized. When alkenes or alkynes are available, they can react with a free radical, forming a new bond between carbon and radical. Alkenes are more reactive than alkynes because the resulting radical is on an sp2 carbon instead of an sp carbon. These are also considered propagation steps because they take one radical and make a new radical. Practically, one of the main radical reactions that we talk about in the standard organic chemistry course is the radical halogenation of an alkane. There aren't typically many reactions we can do to just plain alkanes, so radical halogenations offer an important way to install functionality. These reactions need to be catalyzed by light of sufficient energy, typically in the UV range, so that the initial chlorine can be created. We'll walk through the elementary steps in the reaction in the next slides. The first step is always an initiation, or homolytic cleavage step. In this case, it's the homolysis of chlorine by UV light to produce two reactive chlorines. One reactive chlorine can go through a bimolecular homolytic substitution step, which propagates the radical and creates an HCl byproduct. In theory, the resulting carbon radical could be terminated by the remaining chlorine radical, but there's a lot more molecular chlorine around, and a second bimolecular homolytic substitution to produce the haloalkane and another chlorine radical is a lot more likely. The more chlorine radicals we produce, the more likely we are to have them meet each other or another carbon radical. In either case, the product is much more stable than the reactants, and the reaction will quickly terminate. It's easy to think about the reaction more or less as discrete steps, like in the bromination or chlorination of an alkene, but the reality is that much of the radical is produced through propagation rather than termination. Very little actual radical needs to be formed initially for the reactant to react toward completion. When we look at relative rates of other halogens using the same mechanism, we actually have several bond dissociation energies to think of when we look at the overall net reaction. The halogen bond dissociation energy often determines how fast the reaction goes, since it's always endergonic. However, the stability of the carbon-halogen bond and the hydrogen-halogen bond can also end up releasing lots of energy. That's why even though fluoride radicals are readily accessible and react fairly quickly, they aren't typically used. The carbon-fluoride bonds that are formed are too stable, and we'd all die in the explosion. The overall reaction coordinate diagram helps to give some pictorial context. Fluorine dissociates easily, but also associates easily. Huge problem because we have a very largely exergonic reaction. It's very difficult to control. Chlorine does the same thing, but releases energy much less, and for that reason is much more useful on a lab scale. Bromine doesn't actually dissociate or associate as easily, which means that bromine tends to seek out the most stable radical in ways that chlorine doesn't need to, and actually ends up being very selective in its locations. This difference can be useful as we seek specific halide products. Bromine will give almost entirely the halogen at the location of the most stable radical, which you can see as the 99% yield of the 2-bromopropane below. While chlorine gives a mixture of products, which you can see in the mixed yields between 2-chloropropane, about 60%, and the less stable primary halide at 40% of 1-chloropropane. But chlorination can sometimes be the only direct way of producing a primary halide. In both bromination and chlorination, the radical is still more stable on the secondary carbon, but because the chlorine is more reactive to begin with, the selectivity is not as significant for secondary over primary. For reference, the relative selectivity for chlorination of tertiary to secondary to primary is 6 to 4.5 to 1. In contrast, bromination is selective at a 19,000 to around 300 to 1 ratio. So why do we still see so much of the primary product in chlorination when the secondary is more stable? It has everything to do with the total number of hydrogens that could give us the desired product. There are 6 hydrogens that could give us a primary product, but only 2 that could give us a secondary product. Remember that for a reaction to occur, we need collisions, but also collisions with sufficient energy. The number of available hydrogens makes a collision much more likely, even while the lower reactivity makes all of those collisions less likely to have sufficient energy to yield a product. In radical halogenations, the same homolytic cleavage needs to occur for either reaction, either at a secondary or primary position. So if we look at just the formation of the carbon radical, the shape of the reaction curve for that step can give us an understanding of the difference in selectivity. Chlorination is exergonic at that differentiating step, which means that the transition state is mostly similar to the reactants, and there's much less difference in energy. It becomes much less selective. Bromination is endergonic at the differentiating step, which means that the transition state is mostly similar to the radical intermediates, and there's a much larger difference in energy for the transition states, and it becomes much more differentiating between those transition states. Getting these reactions to actually occur is much more complicated when we're radically halogenating alkenes. Typically, molecular bromine is required to generate the bromine radical, but molecular bromine can also react via electrophilic addition, and it reacts much more quickly. Almost no radical product is formed under these circumstances. To avoid this, instead of using molecular bromine directly, NBS is used to supply a radical initiator and then a consistent low level of Br2 to supply the Br to the resonance stabilized radical that would form and propagate as a bromine radical. Radical reactions with bromine supplied by NBS begin by homolysis of the weak NBr bond. The resulting bromine radical readily extracts the most reactive hydrogen, forming HBr. The strong acid, HBr, forces a tautomerization of another NBS, which can create an electrophilic bromine, which then can get picked up by the bromide to form a Br2. After the bromine is gone, it doesn't really matter what happens to the succinimide, but it can tautomerize back to the diamide form after bromonium is released, in case you were worried about it. Notice that we've created a carbon radical, which will likely go through bimolecular homolytic substitution with any molecular bromine. It'll take a bromine off and leave a bromine radical. And of course, the bromine radicals could also react with this carbon radical directly, but this is going to happen a lot more seldomly at a lot lower radical concentrations. The Br2 will be at a steady low concentration to react with it.